Let's explore the power and current calculations for different three-phase heater configurations. We'll analyze 4 scenarios involving 4,500 watt heaters designed for 230 volts. The key here is understanding how the heaters are connected, whether in series, parallel, or a combination of both. Scenario 1 features 3 heaters connected in series in a delta configuration. In this setup, the total wattage is 4,500 watts. The current draw per heater is 20 amps. The heaters are in series across the 3 phases. This means that the voltage across each heater is 230 volts, and the current through each heater is the same. Scenario 2 involves 3 heaters connected in parallel in a Y configuration. The total wattage for this setup is 13,500 watts. The current draw per heater is 60 amps. With the heaters in parallel, each heater experiences the full 230 volts. The current through each heater sums up to the total current. Scenario 3 presents a combination of series and parallel connections in what is referred to as a delta Y configuration. Here, 2 heaters are in series and 1 heater is in parallel. The total wattage is 9,000 watts. The current draw for each of the series heaters is 40 amps. The current draw for the parallel heater is 20 amps. The 2 series heaters share the voltage, hence the higher current compared to the single parallel heater. Finally, Scenario 4 illustrates another combination of series and parallel connections, this time in a Y-delta configuration. 2 heaters are connected in parallel, and this parallel combination is then connected in series with another heater. The total wattage remains at 9,000 watts. The current draw for each of the parallel heaters is 40 amps. The current draw for the series heater is 20 amps. The parallel heaters divide the current, while the series heater carries the combined current of the parallel pair. Now it's very important to understand that the square root of 3, which is approximately 1.732, is not directly used to calculate three-phase power in these specific scenarios. It's also important to understand that the root 3 is typically used to convert between line-to-line voltage and line-to-neutral voltage in balanced three-phase systems. These calculations assume balanced conditions where each phase carries an equal load. In unbalanced systems, more complex calculations may be necessary. The power calculations are based on the formula power equals voltage times current adjusted for the specific configuration. For series connections, the voltage is divided among the components while the current remains the same. For parallel connections, the voltage is the same across all components, while the current is divided. In practical applications, factors such as voltage drops and component tolerances should be taken into account. Also, it is critical to adhere to all relevant electrical codes and safety standards when working with three-phase systems. These examples showcase how different wiring configurations impact power distribution and current flow. The choice of configuration depends on the specific application requirements and available voltage levels. When designing three-phase heater systems, consider factors such as desired heating capacity, voltage requirements, and current limitations. Proper wiring techniques and safety precautions are essential for reliable and safe operation. Understanding these fundamental concepts enables you to effectively analyze and design three-phase heater systems for a variety of applications. Remember to always consult with qualified electrical professionals for complex installations or when working with high-voltage systems. Let's delve a little deeper into the fundamental principles behind these calculations. To begin, it's important to clarify the relationship between power, voltage, and current. Power, measured in watts, is the rate at which energy is transferred. Voltage, measured in volts, is the electrical potential difference that drives the current. Current, measured in amps, is the flow of electrical charge. These 3 quantities are related by the formula power equals voltage times current, often written as P equals V times I. In a single-phase alternating current circuit, this formula is straightforward to apply. However, in three-phase circuits, the calculations become more complex due to the presence of multiple phases and the different ways in which these phases can be connected. The 2 primary types of three-phase connections are delta and Y, also known as star. In a delta connection, The three phases are connected in a closed loop, forming a triangle. The voltage between any two phases, known as the line-to-line voltage, is equal to the voltage across each phase winding. The current in each phase winding, known as the phase current, is related to the line current by a factor of the square root of 3. In a Y connection, the three phases are connected to a common neutral point, forming a star shape. The voltage between each phase and the neutral point, known as the line-to-neutral voltage, is related to the line-to-line voltage by a factor of the square root of 3. The current in each phase winding is equal to the line current. Now let's revisit the four scenarios presented earlier, keeping these principles in mind. In scenario 1, three heaters are connected in series in a delta configuration. Since the heaters are in series, the same current flows through each heater. The total voltage across the three heaters is equal to the line-to-line voltage, which is 230 volts in this case. Therefore, the voltage across each heater is 230 volts divided by 3, which is approximately 76.7 volts. The current through each heater can be calculated using the formula I equals P divided by V, where P is the power rating of the heater, which is 4,500 watts, and V is the voltage across the heater, which is 76.7 volts. This gives a current of approximately 58.7 amps. However, it's important to note that this calculation assumes that the heaters are purely resistive loads. In reality, heaters may have some inductive or capacitive reactance, which would affect the current flow. In scenario 2, three heaters are connected in parallel in a Y configuration. Since the heaters are in parallel, the voltage across each heater is the same, which is equal to the line-to-neutral voltage. The line-to-neutral voltage is related to the line-to-line voltage by a factor of the square root of 3. In this case, the line-to-neutral voltage is 230 volts divided by the square root of 3, which is approximately 132.8 volts. The current through each heater can be calculated using the formula I equals P divided by V, where P is the power rating of the heater, which is 4,500 watts, and V is the voltage across the heater, which is 132.8 volts. This gives a current of approximately 33.9 amps. The total current drawn from the three-phase supply is 3 times the current through each heater, which is approximately 101.7 amps. In scenario 3, two heaters are connected in series, and one heater is connected in parallel in a delta Y configuration. The two series heaters are connected in series across two phases of the delta connection. The voltage across these two phases is equal to the line-to-line voltage, which is 230 volts. Therefore, the voltage across each series heater is 230 volts divided by 2, which is 115 volts. The current through each series heater can be calculated using the formula I equals P divided by V, where P is the power rating of the heater, which is 4,500 watts, and V is the voltage across the heater, which is 115 volts. This gives a current of approximately 39.1 amps. The parallel heater is connected between one of the phases and the neutral point of the Y connection. The voltage across the parallel heater is equal to the line-to-neutral voltage, which is 132.8 volts. The current through the parallel heater can be calculated using the formula I equals P divided by V, where P is the power rating of the heater, which is 4,500 watts, and V is the voltage across the heater, which is 132.8 volts. This gives a current of approximately 33.9 amps. In scenario 4, two heaters are connected in parallel, and one heater is connected in series in a Y delta configuration. The two parallel heaters are connected in parallel between one of the phases and the neutral point of the Y connection. The voltage across each parallel heater is equal to the line-to-neutral voltage, which is 132.8 volts. The current through each parallel heater can be calculated using the formula I equals P divided by V, where P is the power rating of the heater, which is 4,500 watts, and V is the voltage across the heater, which is 132.8 volts. This gives a current of approximately 33.9 amps. The series heater is connected in series with the parallel combination across two phases of the delta connection. The voltage across these two phases is equal to the line-to-line voltage, which is 230 volts. The current through the series heater is equal to the total current through the parallel combination, which is 2 times the current through each parallel heater, which is approximately 67.8 amps. The voltage across the series heater can be calculated using the formula V equals P divided by I, where P is the power rating of the heater, which is 4,500 watts, and I is the current through the heater, which is 67.8 amps. This gives a voltage of approximately 66.4 volts. It's important to remember that these calculations are based on ideal conditions and may not accurately reflect the actual performance of the heaters in a real-world application. Factors such as voltage drops in the wiring, variations in the heater resistance, and imbalances in the three-phase supply can all affect the power and current distribution. Therefore, it's always a good idea to measure the actual voltage and current values in the circuit to verify the calculations and ensure that the heaters are operating within their specified limits. Furthermore, it's crucial to adhere to all relevant electrical codes and safety standards when working with three-phase systems. Improper wiring or overloading of circuits can lead to dangerous conditions such as overheating, electrical shock, and fire. Therefore, it's always best to consult with a qualified electrician to design and install three-phase heater systems. In addition to the 4 scenarios discussed above, there are many other possible configurations for three-phase heaters. The optimal configuration for a particular application will depend on a variety of factors such as the desired heating capacity, the available voltage levels, and the current limitations of the wiring. By understanding the fundamental principles of three-phase power and the different types of three-phase connections, you can effectively analyze and design three-phase heater systems for a wide range of applications. Remember to always prioritize safety and consult with qualified professionals when working with electrical systems. Finally, the NEC, or National Electrical Code, provides guidelines for safe and effective electrical installations, including those involving three-phase systems and heating equipment. The NEC covers various aspects such as conductor sizing, overcurrent protection, grounding, and wiring methods. For example, NEC Section 310.15 provides tables for determining the allowable ampacity of conductors based on their size, insulation type, and ambient temperature. These tables help ensure that conductors are not overloaded, which can lead to overheating and fire hazards. NEC Section 240.4 specifies the requirements for overcurrent protection, such as circuit breakers and fuses. Overcurrent protection devices are designed to protect conductors and equipment from excessive current flow, which can be caused by short circuits or overloads. NEC Section 250 provides detailed requirements for grounding electrical systems. Grounding helps to minimize the risk of electrical shock and provides a path for fault current to flow back to the source, allowing overcurrent protection devices to trip and de-energize the circuit. NEC Section 424 covers the installation requirements for fixed electric space heating equipment, including heaters. This section addresses issues such as clearances, wiring methods, and control devices. When designing and installing three-phase heater systems, it's essential to comply with all applicable NEC requirements. Failure to do so can result in safety hazards and code violations. It's also important to consult with local electrical inspectors to ensure that the installation meets all local requirements. In conclusion, understanding the principles of three-phase power, the different types of three-phase connections, and the relevant NEC requirements is crucial for designing and installing safe and effective three-phase heater systems. By following these guidelines, you can ensure that the heaters operate reliably and safely for their intended purpose.